Good morning, everybody. So, I will begin. Appreciate you folks who are joining me. Of course, everybody else will get the recording, but that's okay. Nevertheless, let me go over. I'm trying not to go overly detailed, and I have a couple of handout things that I'll include on the blackboard at the bottom of week 2 because I had to redo the blackboard this year because we're using the Cowan textbook. So, it didn't come there initially. So, I join the party. So I try to keep an eye. If anybody's dinging, if somebody looks like they want to be let in, let me know. I'm going to have my thing on. So here we go. I'll show you what I'll be sending to you. I do have an outline from some additional notes here that when we get to this with regard to viruses, I sort of stuck them on top of this existing outline that I have to put on as well. And you can see it here. Okay. That's all of these different, different structures and things like that and classifications, which is really what we're going to go into with this chapter, how they enter and what are the distinction between what are called latent, persistent, acute infections. Really, chronic and persistent are fairly similar. Complex infections, which is really our HIV discussion, tumors that are there, and certain amounts of genomic exchange. Like I said, I'm not really dealing with the plant viruses and things like that. So that's one document that I'll include. And the other one is, and I always write it on the board. So I got to the point where I started, and it's the fact that we have all these herpes viruses, which I don't know that we'll get to today, but at least I'll be at a point of introducing it because there's a certain degree of lack of completion on the Cowan PowerPoint with regard to the different DNA and RNA viruses that they explore. But let me begin. So that's the introductory note. So I have this cooked up for a little bit later, and here is, and we'll get to where we came through with that before. Organization. We may have a dog interruption. Very possible, but we'll see. I can hear him. Okay, now I heard her. There are students listening in as you're criticizing. I can't show them. What do you get into? Oh, yeah. Oh, he loves those. Darn you, doofus. Oh, oh, that's not the first hat he's grabbed. Okay. He's. Hold on. Oh, hold on. Whoa, 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 whoa. I've got people online. Go wait. Go wait. Sorry, everybody, for this degree of insanity. Here, look. He chewed the hat. He's a hat chewer. My wife is sewing hats for goose clothes, or this was a hat for an existing goose clothes outfit. I just want you to know that. For those of you who have not turned it off and are listening, this is why he's in trouble. He is in trouble. All right, everybody. Sorry for the interruption. We had a dog-oriented interruption for anybody who has just joined us. Here we go. So this is kind of where we started from last time. It's a little bit crazy. And this was the idea. We have a capsid, and it's called a nucleocapsid when you have the combination of whichever genetic material. And to me, the first big distinction is what I left you with last time was the relationship, not the relationship, but the distinction between enveloped and naked, or what they call non-enveloped viruses. And it's a very good illustration here in the Cowan book that shows you, and they've changed the classifications a little bit about these, but we'll look at them and explore them. But these are examples of, this is what are called isometric viruses, because all of the sort of the materials, this is that very, very famous, called an icosahedron. It's got 20 individual capsid proteins. You can see these circular proteins that are there. And it's like a 20-sided die made of equilateral triangles. And you can see the genetic material that's inside. The distinction and why these are such a pain. This is a very simple unit. You have genetic material, you have a very secure protein enclosure, and you have these spikes. And it's those spikes that attach to the receptors on whatever cells. So let's say it's the common cold. That's going to be respiratory lining cells. Very simply. The distinction here, now we have the same kind of capsid, we have the same kind of genetic material, but yet we have an envelope effectively made out of the material that's from the cell membrane. The cell membrane, okay, and what basically the virus does when it's replicating inside the cell, it sort of spit out, and as it spit out, it grabs onto a piece of membrane. And what has been implanted in the membrane are the protein spikes. So now this is another way. Now, the distinction between this is because the spikes are inherently part of the membrane. If you can destroy the membrane, then all you're left with is a nugget inside, and that can't attach because it's all about receptors. That's the specificity. It goes back to the first part of A and P when we started to look at the cell. Receptors are very specific. Okay, the different embedded proteins, the ones that act as receptors, only attach to something that they're basically designed to attach to. And that gives you the specificity of the protein spikes. That's the way it's spread. That's the range, the different number of species, etc. So the capsid. Really, when I talk about the capsid, I'll talk about its shape or its architecture or its capsid structure. That's one of the features that you need to be remembering. Okay, so it's very, very prominent. Again, the individual units are called capsomeres. I've seen it misspelled as capsimers. Doesn't matter, they're the same thing. And they spontaneously self assemble. And years ago, you'll see it in Oddball very shortly, but there used to be considered three categories. You had the helical, which we'll look at, the icosahedral, which I just talked about, and you have what we used to call pleiform, or and the term complex was used. Pleiform literally meant some other form. So typically in viruses that affect us, if it wasn't a classic helical or icosahedral, we called it pleiform. Not doing too much today. Complex is very much a form, and is used for the phage viruses, very similar to the one you saw in that animation of transduction. So, but for the time being, we're just going to classify them as either helical or icosahedral, and the bulk of them certainly are icosahedral. Okay, the enveloped viruses. So, there's three ways we classify. Let me preface it. Genomically, is it DNA or RNA? So it's one of those two categories. Is it enveloped or naked? Category number two. Is it icosahedral or helical? Category number three. Those are things that you should recall on specific viruses that we talk about a lot. So when we talk about the common cold, a rhinovirus, it's a naked or non-enveloped virus. It's an RNA virus when you're talking specifically about rhinoviruses. And it's naked RNA and it's icosahedral. Very simple. It's not the only one that falls in that category. There are plenty. So an enveloped virus, as it leaves, it pinches off a little piece of the cell membrane. Okay. Sometimes the nuclear envelope conceivably could be part of that. Maybe some part of the endoplasmic reticulum conceivably, but they shouldn't have an endoplasmic reticulum necessarily, but they could. Okay. More flexible than the capsids, so enveloped viruses typically have more additional shapes. And that's where the pleomorphic term comes from. So it's a little better understanding of what pleomorphism is. Not that that's a big deal for you. So what makes it helical? Helical capsules, rod shape. It's the arrangement. If you look at it closely here's the nucleic acid in a very much of a linear form, and the capsid surrounds it. So you can see that's the very famous tobacco mosaic virus. That's there. So the capsuleers bond together a series of hollow discs because it's hollow in the middle. That's where the genetic material is. Bracelet's a good way to describe it. Okay, they link together with other discs and a continuous helix is formed that's there. Very rigid, tightly wound, cylindrical shape. That's the tobacco mosaic that's there. So that's a plant that particular virus is attacking. Again, they can attack all different life forms. Enveloped helical nucleocapsids are a bit more flexible. Okay, tend to be arranged as looser helix within the envelope. Type of morphology is found in several enveloped human viruses. So what you're going to see is it's a little bit different. So you're going to see influenza and measles and parainfluenza, even rabies, which are still technically categorized as helical nucleocapsids. We used to consider the influenza and the measles from categories that were, quote, pleiform. It's a little bit different today. So basically, we're just going to utilize the two for the argument's sake. The icosahedron, you can see the way they spell it, 20-sided figure, 12 evenly spaced corners. That's basically where it is. So you can begin to look at that. Vary. Sometimes there's more than one type of capsamere. You can see polio has 32 and adenovirus has 252. So there's some subtleties there. You don't have to remember those numbers, certainly. But the classic adenovirus or adenovirus, naked icosahedral virus, that's another, by the way, cold virus, in case you're wondering. And we'll get to it. In the photo, you can clearly see the spikes. You can see them there, some of which have broken off, not unusual. Hep B and herpes simplex are enveloped icosahedrons. They're there. Hep B is an oddball now that we've studied it a bit more. We used to be considered in that envelope DNA virus. Now it's kind of made its move into the retrovirus category, and we don't really look at it too much in this course, other than for the sake of completeness. But herpes, we'll spend a bunch of time with. You can see it over here. This is the bacteria. It's a classic bacteriophage. I think this is T4 bacteriophage. That really targets E. coli a lot. And so this is one that we've studied the most. So it's very complex, only in viruses that infect bacteria. Bacteriophage means bacteria eater, by the way, that phage part. They're not on envelope. They're naked viruses. They look just like the diagram. There it is, a micrograph. So you can see the genetic, and effectively what this has become, and I described it to you before when we looked at transduction, pardon me, nothing more than a sophisticated syringe that this whole assembly, the tail fibers are how it braces itself, okay, on the bacteria's external cell wall or envelope, whatever it is. In E. coli would be the outer membrane. The tail fibers are how they penetrate it. Then you have this sheath, you have this collar, and the head. And effectively, this is like a syringe. So it's injecting, because the entirety, when our viruses infect us, as you will see, the entire capsid and the genetic material enter, and it undergoes a process called uncoating. And here, there's just the genetic material being inserted into it. So there's nothing unknown about it. It's just an unusual form. So that's nothing that's coming after you like a giant mosquito in the middle of the night. So the sum of the genetic information is always referred to the genome. Again, DNA or RNA, never both. Very compact, very small. Really, it's a limited set of instructions because the assembly material is already there. You have all the inner workings of the cell that's going to occupy, that it takes over and starts doing stuff. So it doesn't need a whole lot of instruction other than ignore whatever else you're doing and you're going to do this. So hepatitis B, 4 genes. Herpes virus is more complex. So it's whatever to invade the host cells and redirect their activity. Not a lot to it. So hepatitis B is a tremendous, we don't hear about it so much because of the hepatitis B immunization, which interestingly was manufactured, the immunization was manufactured by genetic engineering. So we utilized to combat a microbe, we used microbial technology, interestingly enough, with regard to that as well. So the Hep B immunization has sort of rendered Hep B not totally in the past if you look on a worldwide basis, but in this country, we're much more Hep C oriented, and we'll get into the hepatitis viruses as well. Pardon me. So now you look at the variety of strandedness, and I don't deal with it too terribly much. The ones that we're going to look at are the influenza virus because of its strandedness, because it has 7 to 8 identical single strands of RNA. And that's one we're going to look at because of the complexity issues that are in it. But they're really the ones where we identify the ability to mutate so rapidly. We see it in influenza, and obviously we see it in COVID. So those are the areas that have to do where the strandedness plays a role. But the one to really look at to get an idea of what's going on in something called antigenic drift. Okay, this capacity to mutate, and really what kind of form COVID called antigenic shift. The best teaching model, because best it's understood, is influenza. So DNA virus, single or double. RNA can be double stranded, but more often single stranded. Okay. The sense just means is it ready, how ready it is to use. So positive sense immediately starts to make proteins. Negative sense have to be flipped over to positive to make proteins. And that's something that we talk about briefly called transcription strategy, okay, and replication strategy, but that's not something I spend a lot of time with other than HIV because it speaks to its complexity and why we have to use multiple antivirals to treat it. Here's the segmented, okay, and the retrovirus is interesting in and of itself, and we do spend, and we'll do that in class time as opposed to online. This is almost like a draw out kind of a thing, kind of how it works to see this replication strategy and where we interfere with it with regard to antivirals. And what's uniquely in that package is what defines it as retrovirus is a particular enzyme to do the retrovirus, which means convert it from RNA to DNA and then goes back again. And then other enzymes that are in there to facilitate the manufacture inside the cell. So this is where I take a little bit of issue. They're just giving you examples. I'm going to give you a list. And the list is really the next part of this discussion that's coming up. That's there. So, for instance, they're just giving you examples. Double-stranded DNA, variola, known as smallpox. We talked about it historically with regard to Jenner's work. We'll mention it for the sake of completeness. To me, it looks more linear in this regard rather than isometric. So I think today that we used to consider this to be the oddball, but now this is just a variation of the helical virus. Herpes simplex, very famous. This is herpes 2, general herpes. You could see that handout. I'm going to go over it in detail. There's a lot there. And we talked about it already a little bit. Parvo. Erythema infectiosum. We'll get into what it is. Very interesting disorder. I'll talk about it shortly. So it's single-stranded DNA. So it's an oddball versus double-stranded DNA that's here and single-stranded DNA. RNA. Polio. Spend some time on that. That's in another category called enteroviruses because they enter by way of our enteric system, meaning our gut. Influenza. Very, very famous. Rotavirus, talk about that with GI stuff, and there's the aforementioned HIV. And you can see the diseases it causes, and that's kind of what we're going to do. The way I typically set this up is we talk about the categories, which I'm going to flip to the Nestor PowerPoint and show you the categories. We'll give you not pretty much the common name for the virus, and we'll look at a little bit of the diseases that it causes. We will deal more with the specifics of the diseases in the second half of the course where we do the more clinically oriented stuff. For me, the last third or so of the course is chapters that look at the different diseases that affect respiratory, skin, genitourinary, digestive, immune, etc. That's where we're going to look for that. So I don't think there's anything else. Yeah, I don't want to go through all those enzymes just yet, and we'll get back to it. So out we go. And here's the Nestor PowerPoint. And again, I use that mostly because I'm so familiar with it, and I love the table that's in it, and we're coming to the table. So we do not do this. We are not doing the taxonomy. Okay. You can see as of 8, more now, I'm sure, all the different things. And they're, again, characterized by nucleic acid, strandedness, host, shapes, blah, 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 blah. The easy way. We're going to look at this chart. This is DNA viruses. Then we're going to come back over here and look at RNA viruses, which magically there's 2 pages of, lucky you. This is, the naming is interesting. I'm going to go back to those other slides because that's really where we're going to spend a lot of time. There's not a whole lot, there's more listening and informational stuff on this than anything else. So you have Coronaviridae, meaning a crown. That's how the name got coronavirus, because they looked at the capsid and it looked like a crown. You'll see it. Geographic regions, another one that are there. Where it enters, or its access point. So rhino is nose, entero is the enteric or the alimentary canal. Disease, polio, sometimes different things. We typically just use that name. We get down to the species. So it's a rhinovirus, it's a retrovirus, whatever, with all of those things. This is important. And there's a qualifier. As well as being important, we have to qualify why it's important. The qualifier is this is how the viruses are usually spread, not always spread. So we have, and maybe COVID is good an example. We're not 100% sure. We know it's spread respiratorily. Could it be impactful if we ingest it? Don't know. Could it get directly in your bloodstream by physical contact or an open wound? Could be. And so some of these are spread in more than one way. And as we learn more about them, we understand a little bit. Maybe as good an example of that when we talk about Ebola. So here's Ebola, tremendous killer. Thankfully, there have not been a lot of certainly not in this country, but its effect in sub-Saharan Africa can be dramatic and scary at times. For the longest time, we thought it was contaminated water. We now know that that's not the only way it's spread. And that has all changed the way we treat it. For instance, you're probably not going to be if you go, if many of you, if you choose to do a medical mission or you work in areas, for those who are going into medically oriented or clinically oriented fields like nursing or healthcare related, maybe you go to another country, there's a whole subset of interesting things that go along with that. So that's when you have to really look at what diseases are prevalent and how they spread and the do's and don'ts that are there. So this is another category that has nothing to do, and you're even going to see that some of these categories have subgroups that are in that basically, and one is going to come up in RNA viruses where we have to subgroup them into those that are spread respiratorily and those that are spread enterically. So when we talk about this, groups of unrelated viruses, unrelated is the watchword, fecal to oral, just what it sounds like. Something is passed in feces, whatever you want to. Typically, this is the way when you hear about the quote stomach flu. It's not really influenza, it's an enteric virus. Somehow the virus is passed, somebody doesn't wash their hands, classic way, thoroughly, they're in food service, you contact it, you swallow it, and now you got it. So fecal to oral, oral to fecal, classic. It doesn't mean it's always going to produce gastrointestinal symptoms. Where do we get to polio? Respiratory, self-explanatory, you inhale it. And really it has to do with the lining cells that are where the receptors are located. Zoonotic, this is the unusual one. Classically, from members of the animal kingdom to humans. That's the best way to describe it. They have created an effectively arthropod born. Arthropods are insects. Okay. They're still members of the animal kingdom. So to me it's almost a nonsensical category. I call it zoonotic. You can subcategorize as arbo, and maybe somewhere else you're going to have to know that name, but not for me. Arthropod porn. So if you see it's in a reading and someone says, "Oh, it's an arbovirus," now you know where it's spread. So yellow fever is spread by mosquitoes. That's an arbovirus, but it's also by definition zoonotic. So and a lot of different species. So for instance, yellow fever, dengue, which is interestingly in the same category as yellow fever, as you were going to see in the viruses that they are. Okay. West Nile, which is in that same category. I'm not as familiar with lacrosse encephalitis. So we're going to subcategorize that, and then you can see the full unit that's here. So here they're both zoonoses, but animal in this case, whether it's rabies, you would think about it, an animal bite or cowpox coming directly from a cow, as opposed to these different ones that we're looking at. And Zika, interestingly, in the same category with West Nile and with yellow fever and dengue. And then lastly, here, the one we talk about, sexually transmitted. And it's sexually transmitted is, again, somewhat of a misnomer. You have to think of it's blood and body fluids and close intimate contact. So it doesn't necessarily have to. It can be directly through the blood, like needle sharing. It conceivably could be from some other intimate contact. So close. When we think of a lot of times, uh, viruses, particularly HPV, human papillomavirus, which is so prevalent, that's on the skin. That's intimate skin to skin contact. It doesn't necessarily mean there has to be intercourse, though it certainly could be part of it. That's there. It doesn't mean there have to be passed through the fluids. It doesn't. There's more of a physical or frictional component to that than anything else. And so, and if you even want to think about it with regard to, I'm saying goodbye to my wife. She has to go run to her mom's. Don't mean to interrupt. I'll be in touch. Go ahead. Love you. Goodbye. Hold on. Hold on. I want to see if you're still alive in there. Just saying hello to whoever's there. So I want to make sure it's still recording, and I will come back. So she's heard me do this before. I'm probably boring her to death. Off we go. Back again. So lastly, this is the interesting one to me, because I guess the best way to frame it is it's not always just during intercourse, though it can be. Okay, there's other factors that are involved. I mean, think like a cut. This is for you, particularly those in nursing and any medical field. When you have an open wound, you're not only you at risk of passing something, you're at risk of getting something. So you need to be very, very cautious about this. I think today, to frame it a little bit better, we're much more cognizant of that. I mean, people they're glove crazy and mask crazy now, as far as I'm concerned. I mean, I understand it, but I don't know about you. When I'm driving in my own car, I don't feel that I need to have a mask on. I'm just saying, nor do I have to have gloves on my car, on my steering wheel. Just saying. I know, forgive me. Moving on. I'm back. Okay. I'm going to go backspace here. Here we are. So we will start. You see, there's a lot here. Today, we're going to get through some, not all, of these DNA viruses. And I'm going to paint with a broad brush, which I'd never mind doing. And if I'm going to give you a watchword about DNA viruses, and I talked about it before, it's latency. The problem with what DNA viruses, they're made of DNA. And some of those DNA viruses are going to incorporate with the host cell's DNA. In doing so, they create a mutation, but in doing so, they also can not necessarily demonstrate themselves other than in certain times. That's where latency comes in, or they can alter the cell immeasurably and change it dramatically. And a lot of times that's where cancers come from. So you're going to see some association with DNA viruses. We certainly statistically see more cancers and this stuff. We talk about this virus. I can't even tell you how many times. Okay, at least 3 or 4 times. And that's right here because we're going to talk about how they spread. We're going to talk about it in epidemiology. We're going to talk about it in sexually transmitted diseases. We're going to talk about it in a variety of contexts. This is the first one, and that's HPV, human papillomavirus. It's as common as you want. If you know anybody who ever had a wart, it's human papillomavirus. When we have, that's the major species. In viruses, we have types, and they're typically done numerically. So when we begin to see, when we start talking a little about immunizations in the unit on sexually transmitted genital urinary diseases, as it were, you're going to see they'll talk about the immunization, which originally went under the name of Gardasil, probably still does, from Merck, and it covers X number of types of viruses that are strongly associated with cervical and other carcinomas. So let me give you the backstory here. So it's the same species of virus, not the same type of virus, that will cause a wart on the bottom of your foot, or a wart on your finger, or a genital wart that can be visible on the genitalia, or more difficult to see if it's on the interior of the genitalia, vaginally or cervically. Just trying to give you some context for all of this. So most of them cause warts, most of them, and they're all, not all is the wrong word, they're nearly all could be classified as oncogenic, make a tumor. And that's another misnomer. The word tumor doesn't mean cancer. In some cases, it does. But in the word tumor can be benign as well. And it doesn't, and the fact that it's benign doesn't mean it's not deadly, because most brain tumors are benign, but most of them are deadly because they occupy space. So there's a whole lot of nuances. So you got to be careful when you use the term tumor or oncogenic. But in this particular instance, I'll go back to the same statistic: 15 to 30% of all cancers that we, the human beings, experience are directly related to viral infections because of their oncogenic nature. And in our country, certainly the vast majority come from here. I would dare say 50% come from this area. It is a major problem. We'll start with why and classifications. It's isometric, it's naked, it's a DNA virus. By definition, it is spread by close contact. It does not mean it has to be in the blood. And it does, and while it certainly during intercourse, it would be present in the fluids, it comes from the skin. It is a skin virus. Make no mistake, it does not go deeper in that regard. It infects the stratified squamous epithelia, and it affects both keratinizing and, relatively speaking, non-keratinizing. Okay. It occupies, if you remember your A and P and you go back and look at the skin, the area is called the stratum granulosum. Those have those granular cells. That's where we see evidence of, and that's how you make the diagnosis with a biopsy, of looking at what are called inclusion bodies. Inclusion bodies are something that viruses do, and you can stain them as they incorporate with the host cell's DNA, and in doing so, obviously, they alter it. Voila. That's the whole backstory with regard to that. So, first thing to remember about it, other than it being naked, isometric or icosahedral, and DNA virus, is the fact that it certainly we would classify it as sexually transmitted, close intimate contact, bloodborne, whatever, and the fact that it also has the capacity to cause tumors. That's why, and we're going to look at it when it comes to skin. We're going to look at back and genital urinary. We're going to look at spread. We're going to look at trends. It's really a major player. What the big problem? Why it's so difficult? Is this? It's very difficult to eradicate on surfaces. Mild disinfectants don't do a whole lot with it. Alcohol doesn't do a blessed thing with it, other than mechanically rub it away. So you have to be cognizant of that. Years ago, when I first started to study the classification, they used to call this, they originally extracted, this is nothing you have to know, it's called SV40, simian virus 40. So they identified it in a monkey, okay, some member of the simian related family. And it was called papovaviruses, papilloma, polyoma, vacuolating viruses, how it got its name. Don't have to know that. But now we have a subcategory, and you remember in the skin, you have keratinocytes, you have melanocytes, you have Merkel cells, and you have basically a modified Langerhans cell, which is an immunological cell in nature that samples the environment. This is Merkel cell are the ones that sit on top of free nerve endings. It's an unusual cancer. I don't know enough about it. I'm not going to ask you about it. Mentoring for sake, we used to consider them both at the same time. They are definitely different. Also naked, non enveloped. And then the adenovirus. This is a respiratory infection. Most common colds, when you and I talk about them, are caused by rhinoviruses, which are a naked RNA virus we will get to. There are two other categories of virus at a minimum that cause cold like symptoms. Adeno is probably the next most common after rhino. And for a long time, coronaviruses were in that discussion as well. Not the regular coronavirus, not the mutated ones, okay, that have occurred. So adenoviruses, what's the distinction when we get to respiratory? It's the bad cold. Adeno means gland. And so when you had a cold where you had accompanying swollen glands, more likely to be adenovirus. If you had a bad sore throat, adenovirus. Most colds don't produce a fever, adenovirus ones do. So there are certain distinctions. So these are spread contact or sexually transmitted. This is spread respiratorily, just what it sounds like. Typical. Somebody's got one, just like we were worried about with COVID, maybe cough, you'd be in close proximity. And because it's a naked virus, think of it this way. When somebody coughs, and if they don't cover their mouth, or let's say they're not wearing a mask or anything like that, and it gets on a surface and you touch it, again, you touch your face with your hands if you don't know it was there, and it's going to be on the surface for a while. It doesn't easily deteriorate as the enveloped one, so it's a lot easier for you to come in contact. So once it's on your face, it's easier for you to inhale. Think of it that way. So you can see the look of it. You can see the protein spikes, at least in this particular, because you remember we saw the actual micrograph of it that's there. And there's nothing really that unusual. And there's one more in this category, and here it is. Remember, I mentioned it a couple of times, parvovirus. Well, parvoviruses, and most likely this is spread. I'm not 100, and I won't ask you. It could very well, because of the diarrheal symptoms, be spread that way by some type of fecal to oral route. Perhaps there's also a respiratory component. But this is the condition, and it's only one particular strain that causes it in humans, but most people have had it. And we will look at it. Skin disease is called Fifth's disease. So it's not a proper name, it's a number. When they had skin diseases that caused fever and rash, before we knew the distinction between bacteria and viruses, we ranked them by order of frequency that doctors saw them. And this was back in the 1920s or so. This was the fifth one. It has got a fancy name. It's called erythema, which means redness infectiosum, and it's known as slap cheek syndrome. So what it looks like is the face of, and it's typically little kids 2 to 4 who get a fever, maybe 102, 103, and they get redness on their face. Okay, and it looks for all the world like somebody smacked them. Okay, and and parents are always, oh, I don't want to take them to the doctor because I think I'm hitting my kids. That type of thing. You know, it's all my kids had it. And I wouldn't be surprised if most of you had it when you were kids. Those are the categories of DNA viruses that are classified as naked viruses. And I'm going to give you one more of those and be done for today relatively briefly because, and I just introduced herpes viruses. And we're going to pick that up on Monday. And that's the pox virus category. Again, for the longest time, this now helical virus was thought to be this oddball form. That's because they didn't maintain that shape in the envelope, as we talked about before. These are pox viruses. You had smallpox and you had cowpox. Well, smallpox is very, and again, these are in the same category, but you're going to see they're spread differently. Smallpox is respiratory. Even though it has been eradicated, even though it was the first immunization, we derived the name vaccine. If you remember that discussion in the very first weeks of the class with regard to Jenner, it was one of the greatest killers of all time, and it is still scary if it would ever come back. Okay. Because they stopped immunizing for this. They still have immunizations available. They have samples of the disease because it's a perfect biological weapon, unfortunately. Okay. All of those things are part of it. Cowpox, which because of its being in the same category, was the suitable agent that could be used to stimulate our immune system to fight off the smallpox, is probably spread by contact. Okay. With regard, because milkmaids got it from milking, and they didn't use milking machines, obviously, in the 1700s, didn't have them, and they didn't wear gloves, certainly. Maybe they had some hand protection, I don't know. The reason why we know pox viruses spread that way, there's one that we will cover, interestingly, in either skin and or sexually transmitted diseases, because it's considered both. And that is, and it's got a fancy name. I'm not going to write it out, but I'm sure it'll be in my notes. It's called molluscum contagiosum. So, what's a mollusk? Going back to your basic biology, mollusks are like clams and oysters. And so, why they called it molluscum, it was like it looked like a wart. It was kind of raised and had like a pearly white center. So they thought it was like an oyster appearance. And contagiosum, self-explanatory because it's spread. It is classically speaking, it's kind of like, think of it as like a genital wart, except this one is clearly spread by contact. Okay. And most of the time when we see that, and I've seen them on the foot, from people stepping on where it was on the skin, and this is where a lot of warts come from, on the bottom of the foot, from plantar warts, when they step on something that's rough or abrasive. In the old days, for going out swimming pool, they had burlap. Now they have plastic. It's a little bit different. The burlap would linger on, but the molluscum contagiosum, we typically saw it on the upper inner thighs. So, without getting very graphic about it, think of intimate sexual contact. Think of intercourse, and you get an idea where this would develop. And so that, thankfully, as sexually transmitted diseases go, that particular virus has no severe complications other than cosmetic in nature. And the way it is treated, and what we treated them historically, we would numb them with local anesthetic, and we would basically use an electric needle, doing a process called fulguration, basically inserting a needle and burning it. That's how it was treated. So and it's something. It's a disease that I treated. It's a disease I know people had that was, I treated one on the foot. Somebody else, my first wife had a case of that on the inner thighs. You know, go figure. And it didn't demonstrate on me, so who knows? That was when we were engaged. So we won't go any farther than that. Nevertheless, that leaves us with herpes viruses. And you thought we were done. So here's herpes. It's an innocent looking virus. It's relatively large. It's isometric. Obviously, it's enveloped. It got DNA, good old double stranded DNA. The only eyeball here is the parvovirus that's there. Yet look at this array of problems it causes. And it's an enveloped virus, so we can get rid of it on surfaces fairly easily, just like you can pox viruses. All the rest of these guys are naked viruses. But go back and just introduce it. Let me just show you from that handout that you're going to get. All enveloped, and these, just like HPV, which is associated with cancer and associated with latency. Once you're exposed to HPV, once you have a wart, it doesn't have to be HPV. It doesn't have, I mean, it does have to be HPV. It does not have to be a genital wart. Okay. That virus is part of you. Whether it demonstrates itself again isn't necessarily something that you can know for sure. It may or may not. That is true with herpes viruses. Once you have them, you have them. They don't go away. They reside in latency. Herpes viruses typically, particularly for the ones we know the most about, which are the first three on the list, they become latent and are located in sensory nerve root ganglia. Those are the nodules of nerve cell bodies that lie just outside either the spinal cord or the brain. They're technically part of the peripheral nervous system. So you surely learned about either sensory root or what are called dorsal root ganglia, same thing. And that's where herpetic viruses or herpes viruses. So the name we give to herpes types of infections, or the adjective we use to describe them globally, is called herpetic. They are all enveloped, they are all DNA, they are all latent. Some of them cause cancer as well. So I'll leave you with that, and we'll pick up here in class with this chart and go over this in a little bit more detail and give you some nuances that are part of it, the way that we name them, why they're problems that are there, the long histories, because we know a lot about them. And many of these are ones that have the potential to have impact you or have already impacted you in some way, shape, or form. So thank you very much for your gracious attention is there, and I hope everybody has a great weekend. We'll see you for those that are still awake. Goodbye.